In the vast tapestry of existence, where every discovery seems to unlock 1,000 new questions, what truly lies beyond the veil of our understanding? Imagine gazing up at the night sky, a canvas of shimmering stars and distant galaxies, each a beacon of light carrying secrets billions of years old. Yet, for all the brilliance we perceive, an even greater expanse remains shrouded in mystery, a silent, profound unknown that whispers to the deepest parts of our curiosity. Tonight, we embark on a journey not into what we know, but into the beautiful, bewildering realm of the unknown. 100 profound questions that continue to baffle the brightest minds, inviting us to ponder, to wonder, and perhaps to drift into a peaceful contemplation of the cosmos. Whether you seek to expand your mind with the cutting edge of scientific inquiry or simply find solace in the universe's grand enigmas, allow these mysteries to gently guide you. Let the quiet contemplation of these cosmic puzzles soothe your thoughts, calm your spirit, and lead you into the restorative depths of sleep. Welcome to a journey through the unexplained, where science meets serenity and wonder becomes your lullaby. What is the invisible scaffolding holding galaxies together? For decades, astronomers have observed that galaxies spin too fast, and galaxy clusters hold together with a gravitational pull far stronger than the visible matter within them can account for. This invisible, undetectable substance, which we call dark matter, makes up about 27% of the universe's total mass energy content. It doesn't emit, absorb, or reflect light, making it utterly transparent to our telescopes. Its presence is inferred solely through its gravitational effects on visible matter. Scientists have proposed various candidates, from exotic particles like WIMPs, weakly interacting massive particles, to primordial black holes. But direct detection remains elusive. We know it's there, shaping the cosmos, yet it remains one of the universe's most profound and frustrating secrets, a silent architect of cosmic structure that we can only feel, but never see. What force is accelerating the universe's expansion? Even more mysterious than dark matter is dark energy, an enigmatic force believed to be responsible for the accelerating expansion of the universe. In the late 1990s, observations of distant supernovae revealed that the universe isn't just expanding, its expansion is speeding up. This was a monumental discovery, implying the existence of a repulsive force counteracting gravity. Dark energy is estimated to constitute about 68% of the universe's total mass energy, making it the dominant component of our cosmos. Yet, its nature is completely unknown. Is it a property of space itself, a form of energy inherent to the vacuum? Is it a new type of energy fluid or field that fills space? Or is it a sign that our understanding of gravity, as described by Einstein's theory of general relativity, is incomplete? The quest to understand dark energy is arguably the biggest challenge in modern cosmology, a puzzle that dictates the ultimate fate of the universe. What truly sparked the Big Bang, and what came before it? The Big Bang theory describes the universe's evolution from an extremely hot, dense state, but it doesn't explain what caused this initial state, or what existed before it. It describes the how of cosmic evolution, not the why of cosmic genesis. Was it a quantum fluctuation in a pre-existing void? Was our universe born from the collapse of another? Or is the Big Bang merely a phase in an eternal, cyclical cosmos? Some theories propose a multiverse, where our universe is just one bubble, in an infinite sea of universes. Others suggest a cyclic universe, where big bangs and big crunches follow one another in an endless cosmic dance. The question of cosmic origins remains one of the most profound philosophical and scientific challenges, inviting us to contemplate the very beginning of everything, and perhaps the possibility of no beginning at all. Is time a fundamental river or an emergent property of reality? We experience time as a relentless, unidirectional flow, a constant progression from past to future. But what is time? Is it a fundamental dimension of the universe, like space? Or is it an emergent phenomenon, a product of our perception and the laws of thermodynamics? Einstein's theory of relativity showed that time is not absolute, it's relative, affected by gravity and speed. At the quantum level, the concept of time becomes even more elusive, with some theories suggesting it doesn't exist in the same way we perceive it. Why does time only move forward, never backward? This is known as the arrow of time, and it's deeply connected to the concept of entropy, the universe's tendency towards increasing disorder. But does this fully explain our subjective experience of time's passage? The true nature of time remains a profound mystery, a concept so deeply ingrained in our existence, yet so poorly understood. Are there countless other universes, each with its own laws? The idea of a multiverse, a collection of multiple universes, has moved from the realm of science fiction to a serious topic of scientific inquiry. Several theories in cosmology and quantum mechanics suggest its possibility. Inflationary cosmology, for instance, proposes that the Big Bang was not a singular event, but part of a larger, eternal process that constantly spawns new universes. Quantum mechanics, with its many worlds interpretation, suggests that every quantum measurement causes the universe to split into multiple parallel realities. If the multiverse exists, it would dramatically alter our understanding of cosmic uniqueness and the probability of life. It would mean that every conceivable possibility might exist somewhere in some universe. But how could we ever detect or prove the existence of these other universes? For now, the multiverse remains a captivating yet unverified hypothesis, a cosmic whisper of infinite possibilities. What happens to information that falls into a black hole? Black holes are regions of space-time where gravity is so strong that nothing, not even light, can escape. According to quantum mechanics, information cannot be truly destroyed. However, if something falls into a black hole, it seems to disappear forever, along with all its information. Stephen Hawking famously proposed that black holes emit radiation, now known as Hawking radiation, which would eventually cause them to evaporate. But this radiation appears to be thermal, carrying no information about what fell in. This creates a paradox. If black holes evaporate and the Hawking radiation carries no information, then information is destroyed, violating a fundamental principle of quantum mechanics. Resolving this paradox requires a deeper understanding of quantum gravity, a theory that can reconcile general relativity with quantum mechanics. Until then, the black hole information paradox remains a profound challenge to our understanding of the universe's most extreme objects. What drove the universe's rapid growth in its infancy? The theory of cosmic inflation proposes that in the first tiny fraction of a second after the Big Bang, the universe underwent an incredibly rapid, exponential expansion. This brief period of hyper-expansion elegantly solves several puzzles of the Big Bang model, such as why the universe is so flat and why it appears so uniform on large scales. However, the exact mechanism that drove inflation remains unknown. What was the inflaton field, the hypothetical scalar field responsible for this expansion? What was its potential energy landscape? And what happened when inflation ended, releasing its energy to create the matter and radiation we see today? While inflation is a cornerstone of modern cosmology, its underlying physics remains a deep mystery, a puzzle that holds the key to understanding the universe's very first moments. What colossal gravitational anomaly pulls our galaxy? Our Milky Way galaxy, along with thousands of other galaxies in our cosmic neighborhood, is being pulled towards a mysterious, unseen gravitational anomaly known as the Great Attractor. Located about 150 to 250 million light-years away in the direction of the Hydra Centaurus supercluster, this region exerts a powerful gravitational pull, causing galaxies to stream towards it at speeds of hundreds of kilometers per second. The problem is, when we look in that direction, we don't see enough visible matter to account for this immense gravitational force. The Great Attractor is partially obscured by the plane of our own galaxy, making it difficult to observe directly. While it's likely a massive supercluster of galaxies, its exact nature and mass remain uncertain. It's a cosmic ghost, a gravitational behemoth whose full extent we have yet to map, a reminder that even on the largest scales, the universe is full of unseen forces shaping our cosmic destiny. Where is everyone? Why haven't we found extraterrestrial life? The universe is vast, with billions of galaxies, each containing billions of stars. Many of these stars likely have planets, and some of those planets might have conditions suitable for life. Given the sheer number of potential habitats, it seems statistically probable that life and even intelligent civilizations should be common. Yet, we have found no evidence of their existence. This is the essence of the Fermi paradox. If extraterrestrial life is so likely, why haven't we seen any signs of it? Are we looking in the right places? Is intelligent life incredibly rare? Do civilizations inevitably destroy themselves before they can become interstellar? Or are they deliberately hiding from us? The silence of the universe is a profound and unsettling mystery, a cosmic question that hangs over our search for our place in the cosmos. Is it flat, open, or closed? The geometry of the universe on the largest scales is determined by its total mass energy density. If the density is above a certain critical value, the universe is closed, like the surface of a sphere, and will eventually collapse back on itself in a big crunch. If the density is below the critical value, the universe is open, like a saddle, and will expand forever. If the density is exactly at the critical value, the universe is flat, like an infinite plane, and will also expand forever, but at a decelerating rate. Current observations suggest that the universe is remarkably close to being flat. But why? Is it a mere coincidence, or is there a deeper reason for this specific geometry? The shape of the universe is not just an abstract concept. It dictates its ultimate fate and holds clues about its origin and evolution. It is a cosmic blueprint that we are only just beginning to decipher. Heat death, Big Crunch, or Big Rip? The ultimate fate of our universe is one of the most profound questions in cosmology, and it hinges on the nature of dark energy. If dark energy is a constant property of space, the universe will likely continue to expand forever, leading to a heat death, where all stars burn out, all matter decays, and the universe becomes a cold, dark, and empty void. If dark energy is not constant and weakens over time, gravity might eventually win, causing the universe to collapse back on itself in a big crunch, possibly leading to a new Big Bang. A more dramatic possibility is the Big Rip, where dark energy grows stronger over time, eventually tearing apart galaxies, stars, planets, and even atoms themselves. Each scenario paints a vastly different picture of the universe's final moments, a cosmic endgame that is still being written in the language of dark energy. Why do these ghostly particles have mass? Neutrinos are fundamental particles that are incredibly abundant in the universe, yet they interact so weakly with other matter that trillions of them pass through your body every second without you noticing. For a long time, they were thought to be massless. However, experiments have shown that neutrinos can change from one type to another, a phenomenon known as neutrino oscillation, which is only possible if they have mass. This discovery was a major breakthrough, but it also created a new puzzle. The standard model of particle physics, our current best theory of fundamental particles and forces, predicts that neutrinos should be massless. So, why do they have mass, and what is the mechanism that gives it to them? The answer likely lies in new physics beyond the standard model, a hint that our current understanding of the subatomic world is incomplete. Do isolated north or south poles exist? Every magnet we have ever encountered has both a north and a south pole. If you cut a magnet in half, you don't get a separate north and south pole. You get two smaller magnets, each with its own north and south pole. However, some theories of physics predict the existence of magnetic monopoles, hypothetical particles that have only a single magnetic pole, either a north or a south. The existence of magnetic monopoles would explain why electric charge is quantized, and they are predicted to have been created in the early universe. Despite extensive searches, no magnetic monopoles have ever been found. Are they incredibly rare? Do they not exist at all? Or are we simply not looking in the right way? The search for these elusive particles continues, a quest for a fundamental symmetry in the laws of nature. Are there hidden dimensions beyond our perception? We experience the world in 3 dimensions of space and 1 of time. But some theories of physics, most notably string theory, propose the existence of extra, hidden dimensions. These dimensions are thought to be curled up on a tiny scale, far too small for us to perceive directly. The existence of extra dimensions could explain many of the mysteries of modern physics, such as why gravity is so much weaker than the other fundamental forces. It could also provide a framework for unifying all the forces of nature into a single, elegant theory. But how could we ever detect these extra dimensions? Some experiments at particle accelerators, like the Large Hadron Collider, are looking for indirect evidence of their existence, such as particles disappearing into these hidden dimensions. For now, the possibility of extra dimensions remains a tantalizing yet unproven idea, a hint that our universe might be far richer and more complex than we can currently imagine. Why is the energy of empty space so small? According to quantum field theory, even empty space, the vacuum, is not truly empty. It is filled with a sea of virtual particles that constantly pop in and out of existence, giving the vacuum a certain amount of energy. When we try to calculate the energy density of the vacuum based on quantum theory, we get a number that is astronomically large, about 120 orders of magnitude larger than what we observe from the accelerating expansion of the universe. This enormous discrepancy, known as the vacuum catastrophe, is one of the biggest unsolved problems in physics. It suggests a fundamental flaw in our understanding of quantum mechanics, gravity, or both. Why is the energy of empty space so small? Is there some unknown mechanism that cancels out most of the vacuum energy? The answer to this question could revolutionize our understanding of the universe. Why is there less lithium in the universe than predicted? The Big Bang nucleosynthesis, the theory that describes the formation of light elements in the early universe, accurately predicts the cosmic abundances of hydrogen and helium. However, it predicts about 3 to 4 times more lithium-7 than what astronomers actually observe in old stars. This discrepancy is known as the cosmological lithium problem. Is there a flaw in our understanding of the Big Bang? Are there unknown processes that destroy lithium in stars? Or is there some new physics at play that affects the production or destruction of lithium in the early universe? Resolving this problem could lead to a deeper understanding of the universe's earliest moments and the fundamental processes that shaped its composition. Why do different measurements of the universe's expansion rate disagree? The Hubble constant, a measure of the universe's current expansion rate, is one of the most fundamental parameters in cosmology. However, different methods of measuring it yield significantly different results. Measurements based on the cosmic microwave background, the afterglow of the Big Bang, predict a lower value for the Hubble constant. In contrast, measurements based on observations of nearby supernovae, which act as cosmic distance markers, yield a higher value. This persistent discrepancy, known as the Hubble tension, suggests that there might be new physics beyond our current cosmological model. Is there an unknown particle, a new force, or a modification to general relativity that could resolve this tension? The answer could revolutionize our understanding of the universe's expansion and its fundamental properties. What caused the unexpected deceleration of the Pioneer probes? For years, the Pioneer 10 and 11 spacecraft, launched in the early 1970s, exhibited a tiny, unexplained deceleration as they traveled out of the solar system. This anomalous acceleration, known as the Pioneer anomaly, baffled scientists for decades. Was it a new force of nature, a modification to gravity, or something more mundane? While later analysis suggested that the anomaly was likely caused by anisotropic thermal radiation from the spacecraft themselves. The initial mystery captivated the scientific community and highlighted the importance of meticulously accounting for all known forces when exploring the unknown. It serves as a reminder that even seemingly small discrepancies can sometimes point to profound, new physics. What are the most powerful explosions in the universe? Gamma-ray bursts, or GRBS, are the most energetic explosions in the universe, releasing more energy in a few seconds than the Sun will emit in its entire 10 billion year lifetime. They are observed as fleeting flashes of gamma rays coming from distant galaxies. While we now know that long GRBs are associated with the collapse of massive stars into black holes, and short GRBs are linked to the merger of neutron stars. The precise mechanisms that power these extreme events are still not fully understood. How do these events generate such incredibly powerful jets of high-energy particles? What are the conditions that lead to their formation? GRBs are cosmic beacons probing the most extreme environments in the universe and offering insights into the lives and deaths of massive stars and the formation of black holes. What are these mysterious, fleeting signals from deep space? Fast radio bursts, or FRBS, are incredibly powerful, millisecond-long flashes of radio waves that originate from distant galaxies. First discovered in 2007, their origin has been one of the most perplexing mysteries in astrophysics. Some fast radio bursts repeat, while others are one-off events. What cosmic phenomena could produce such intense brief bursts of radio energy? Proposed explanations range from highly magnetized neutron stars, magnetars, to exotic astrophysical objects, and even, controversially, to signs of extraterrestrial technology. While recent observations have linked some repeating FRBS to magnetars, the full picture of their origin and diversity remains incomplete. FRBS are cosmic enigmas, hinting at extreme physics and perhaps even unknown phenomena in the distant universe. Are there unexplained patterns in the universe's oldest light? The cosmic microwave background, or CMB, is the faint afterglow of the Big Bang, a snapshot of the universe when it was only 380,000 years old. While the CMB is remarkably uniform, tiny temperature fluctuations within it provide crucial information about the early universe. However, some anomalies have been observed in the CMB, such as the cold spot, a large, unusually cold region, and an asymmetry in the power spectrum across the sky. While these could be statistical flukes, some scientists speculate they might be evidence of new physics, such as interactions with other universes, or a non-standard inflationary model. These anomalies challenge our standard cosmological model and push us to consider whether the universe is truly as isotropic and homogeneous as we assume. What are the sources of these high-energy particles? Cosmic rays are high-energy particles, mostly protons and atomic nuclei, that travel through space at nearly the speed of light. They constantly bombard Earth's atmosphere. While we know they originate from outside our solar system, their precise sources remain largely unknown, especially for the highest energy cosmic rays. What are the cosmic accelerators capable of boosting particles to such extreme energies? Supernova remnants, active galactic nuclei, and gamma-ray bursts are all candidates, but no single explanation fully accounts for the observed spectrum and distribution of cosmic rays. Understanding their origin is crucial for unraveling the most energetic processes in the universe. What powers these incredibly luminous objects? Quasars are among the brightest and most distant objects in the universe, emitting enormous amounts of energy, sometimes outshining entire galaxies. We now understand that quasars are powered by supermassive black holes at the centers of young active galaxies, accreting vast amounts of matter. However, the precise mechanisms by which these black holes convert in falling matter into such prodigious amounts of light and radiation are still being studied. How do the jets of plasma emanating from some quasars form and propagate? What triggers their activity? Quasars are cosmic lighthouses, illuminating the early universe and providing clues about the growth of galaxies and their central black holes. How did the universe become transparent again? After the Big Bang, the universe was a hot, dense plasma. As it expanded and cooled, electrons and protons combined to form neutral hydrogen atoms, making the universe opaque to light. This period is known as the Dark Ages. Then, about 1 billion years after the Big Bang, the universe underwent a dramatic transformation, becoming transparent again as hydrogen atoms were rionized. What caused this rionization? The leading candidates are the first stars and galaxies, which emitted intense ultraviolet radiation. However, the exact sources and timeline of rionization are still uncertain. Understanding this epoch is crucial for understanding the formation of the first luminous objects and the evolution of the large-scale structure of the universe. How did galaxies acquire their magnetic fields? Magnetic fields are ubiquitous in galaxies, playing a crucial role in star formation, cosmic ray propagation, and the dynamics of interstellar gas. However, the origin of these large-scale galactic magnetic fields is still a mystery. Were they seeded by tiny magnetic fields in the early universe, which were then amplified by galactic dynamos? Or did they arise from other astrophysical processes? Understanding the origin and evolution of galactic magnetic fields is essential for a complete picture of galaxy formation and evolution. How can particles be linked across vast distances instantaneously? Quantum entanglement is one of the most bizarre and counterintuitive phenomena in quantum mechanics. It describes a situation where two or more particles become linked in such a way that they share the same fate, regardless of the distance separating them. If you measure a property of one entangled particle, you instantly know the corresponding property of the other, even if they are light years apart. Einstein famously called this spooky action at a distance. This instantaneous correlation seems to violate the principle that nothing can travel faster than light. While experiments have repeatedly confirmed entanglement, its underlying mechanism and implications for our understanding of reality remain deeply mysterious. Is it a form of communication, or simply a correlation that transcends classical notions of space and time? How does observation affect quantum reality? In quantum mechanics, particles exist in a superposition of states, meaning they can be in multiple places or have multiple properties simultaneously. However, when we observe or measure a particle, it collapses into a single, definite state. This is the measurement problem. What constitutes a measurement? Does consciousness play a role? Is there a fundamental process that forces a quantum system to choose a single reality? Different interpretations of quantum mechanics offer different answers, from the Copenhagen interpretation, which states that the act of measurement causes the collapse, to the many worlds interpretation, which suggests that all possible outcomes occur in different universes. The measurement problem highlights the profound philosophical implications of quantum mechanics and its challenge to our classical understanding of reality. How can light and matter be both a wave and a particle? One of the most fundamental and perplexing concepts in quantum mechanics is wave-particle duality. It states that all particles, including photons, light particles, and electrons, exhibit properties of both waves and particles. Light, for example, can behave as a wave when it diffracts and interferes, but as a particle when it interacts with matter, like in the photoelectric effect. Similarly, electrons, which we typically think of as particles, can also exhibit wave-like behavior. How can something be both at once? This duality challenges our classical intuition, which forces us to categorize phenomena as either one or the other. It suggests that reality at the quantum level is far more fluid and ambiguous than our everyday experience suggests. A constant dance between two seemingly contradictory natures. Is there a link between consciousness and quantum mechanics? Some physicists and philosophers have speculated about a potential connection between consciousness and quantum mechanics. The idea is that the mysterious role of the observer in quantum measurements might be linked to the phenomenon of consciousness itself. Could consciousness be a non-physical entity that interacts with the quantum realm, causing wave functions to collapse? Or is consciousness an emergent property of complex quantum processes within the brain? While highly speculative and controversial, these ideas explore the deepest connections between the subjective experience of being and the fundamental nature of reality. It's a frontier where science, philosophy, and spirituality often intersect, pushing the boundaries of what we can even conceive. Is it a force, a curvature, or something else entirely? In Newton's classical physics, gravity is described as a force that attracts objects with mass. Einstein's general relativity revolutionized this understanding, describing gravity not as a force, but as a curvature of spacetime caused by the presence of mass and energy. Objects move along the shortest paths in this curved spacetime, which we perceive as gravity. However, general relativity, a classical theory, struggles to reconcile with quantum mechanics, which describes the other fundamental forces. The quest for a theory of quantum gravity aims to unify these two pillars of modern physics, describing gravity at the quantum level. Is gravity mediated by a hypothetical particle called the graviton, or is it an emergent phenomenon arising from deeper quantum processes? The true nature of gravity remains one of the biggest challenges in theoretical physics, a cosmic dance that shapes the universe from the smallest particles to the largest structures. Are protons truly stable, or do they eventually decay? Protons are fundamental particles that make up the nuclei of atoms. According to the standard model of particle physics, protons are absolutely stable and do not decay. However, some grand unified theories, which attempt to unify the strong, weak, and electromagnetic forces, predict that protons should eventually decay, albeit with an incredibly long half-life, far longer than the age of the universe. If protons were to decay, it would mean that all matter in the universe would eventually dissolve, leading to a very different ultimate fate for the cosmos. Despite extensive experiments searching for proton decay, no evidence has ever been found. This absence of evidence places strong constraints on these grand unified theories, but the question of proton stability remains a profound one, touching upon the very permanence of matter. What lies beyond our current understanding of particles? The standard model of particle physics is an incredibly successful theory, describing the fundamental particles and forces that govern the universe, with the exception of gravity. It has been confirmed by countless experiments, including the discovery of the Higgs boson. However, the standard model is incomplete. It doesn't explain the existence of dark matter and dark energy, the masses of neutrinos, the asymmetry between matter and antimatter in the universe, or the nature of gravity. These limitations suggest that there is new physics beyond the standard model, a deeper, more comprehensive theory waiting to be discovered. What new particles or forces might exist? The search for answers drives experiments at particle accelerators and observations in cosmology, pushing the boundaries of our knowledge into the subatomic realm. Why do particles have the specific masses they do? The Higgs mechanism, confirmed by the discovery of the Higgs boson, explains how fundamental particles acquire mass by interacting with the Higgs field. Particles that interact more strongly with the Higgs field have more mass, and those that interact weakly have less. However, the Higgs mechanism doesn't explain why particles have the specific masses they do. Why is an electron so much lighter than a top quark? Why do neutrinos have such tiny masses? These specific values are fundamental parameters of the Standard Model, but their origin remains a mystery. Is there a deeper theory that predicts these mass values from first principles? The question of the origin of mass is a profound one, hinting at a more fundamental layer of reality that we have yet to uncover. Does every particle have a heavier partner? Supersymmetry, or SUSY, is a theoretical extension to the Standard Model that proposes that every known fundamental particle has a heavier superpartner. For example, the electron would have a superpartner called the selectron, and the photon would have a photino. If supersymmetry exists, it could solve several outstanding problems in physics, such as explaining the existence of dark matter if the lightest superpartner is stable and helping to unify the fundamental forces. However, despite extensive searches at particle accelerators, no superpartners have been discovered. If SUSY exists, where are these particles? Are they too heavy to be produced by current accelerators? Or is supersymmetry a beautiful but ultimately incorrect theory? The search for supersymmetry continues, a quest for a deeper symmetry in the laws of nature. Can all fundamental forces be unified? The Standard Model describes 3 of the 4 fundamental forces: the strong, weak, and electromagnetic forces. Gravity remains separate. Grand Unified Theories, or GUTS, are theoretical frameworks that attempt to unify these 3 forces into a single, more fundamental force at very high energies, such as those that existed in the early universe. If a GUT is correct, it would imply that these seemingly distinct forces are merely different manifestations of a single underlying force. GUTS also predict phenomena like proton decay and the existence of magnetic monopoles. While no definitive GUT has been experimentally confirmed, the quest for unification remains a powerful driving force in theoretical physics. A search for the ultimate simplicity and elegance in the laws that govern our universe. Is there a single theory explaining all physical phenomena? The ultimate goal of theoretical physics is to find a theory of everything, a single, coherent theoretical framework that describes all fundamental forces and particles in the universe, including gravity. This would unify general relativity with quantum mechanics and provide a complete description of physical reality. String theory and M theory are leading candidates for a theory of everything, proposing that fundamental particles are not point-like but tiny, vibrating strings or membranes. However, these theories are still under development and lack experimental verification. The search for a theory of everything is a monumental undertaking, a quest for the ultimate understanding of the cosmos, a dream of physicists for centuries, the last unsolved problem of classical physics. Turbulence, The chaotic and unpredictable motion of fluids is a phenomenon we encounter every day, from swirling coffee to raging rivers and atmospheric storms. Despite its ubiquity, a complete theoretical understanding of turbulence remains one of the last great unsolved problems of classical physics. The Navier-Stokes equations, which describe fluid motion, are notoriously difficult to solve for turbulent flows. Why does turbulence arise? How does energy cascade from large eddies to small ones? Can we predict its behavior? A complete theory of turbulence would have profound implications for fields ranging from weather forecasting and aerospace engineering to climate modeling and medicine. It's a reminder that even in the realm of classical physics, deep mysteries still lurk. The unpredictable nature of deterministic systems. Chaos theory deals with systems that are highly sensitive to initial conditions, meaning a tiny change at the beginning can lead to vastly different outcomes later on. This is often described as the butterfly effect, where a butterfly flapping its wings in Brazil could theoretically cause a tornado in Texas. Chaotic systems are deterministic, meaning their future behavior is fully determined by their initial state, but they are practically unpredictable over long periods due to our inability to measure initial conditions with infinite precision. From weather patterns to population dynamics, chaotic systems are everywhere. Understanding chaos helps us to appreciate the inherent unpredictability of many natural phenomena and the limits of our ability to forecast the future. Quantum forces from empty space. The Casimir effect is a fascinating quantum phenomenon, where two uncharged, parallel conducting plates placed very close together in a vacuum experience a small, attractive force. This force arises from the quantum fluctuations of the electromagnetic field. In essence, the vacuum between the plates restricts the wavelengths of virtual photons that can exist there, leading to a slight imbalance in the radiation pressure compared to the outside. This tiny force, predicted by quantum theory, has been experimentally verified. It demonstrates that even empty space is a hive of quantum activity, capable of exerting real, measurable forces. The Casimir effect is a tangible manifestation of the strange and counterintuitive nature of the quantum vacuum, light from collapsing bubbles. Sonoluminescence is the astonishing phenomenon where sound waves in a liquid create tiny bubbles that rapidly collapse, emitting short flashes of light. The temperatures and pressures inside these collapsing bubbles are incredibly extreme, reaching thousands of Kelvin and hundreds of atmospheres. But the precise mechanism by which these bubbles generate light is still a subject of debate. Is it due to shock waves, microjets, or some more exotic quantum effect? Sonoluminescence is a miniature, tabletop experiment that produces conditions akin to those found in stars, offering a window into extreme physics and the mysteries of energy conversion. A mysterious atmospheric electrical phenomenon. Ball lightning is a rare and unexplained atmospheric phenomenon that appears as a luminous, spherical object, typically a few centimeters to a few meters in diameter. It is often associated with thunderstorms, but can appear in clear skies. Unlike regular lightning, ball lightning can persist for several seconds, move slowly, and sometimes pass through solid objects or appear indoors. Despite numerous eyewitness accounts and some laboratory experiments, its exact nature remains a mystery. Is it a plasma phenomenon, a chemical reaction, or something else entirely? ball lightning is a captivating reminder that even in our own atmosphere, there are still natural phenomena that defy easy explanation. Is it possible to achieve fusion at room temperature? Nuclear fusion, the process that powers the sun, involves fusing atomic nuclei to release enormous amounts of energy. On Earth, achieving controlled fusion requires incredibly high temperatures and pressures, typically found in massive experimental reactors. However, the concept of cold fusion proposes that nuclear fusion could occur at or near room temperature, a claim that gained notoriety in 1989, but was largely discredited due to irreproducible results. Despite the scientific consensus, some researchers continue to explore the possibility of low-energy nuclear reactions, LENR, hoping to find a way to harness fusion power without extreme conditions. If cold fusion were ever proven to be real and controllable, it would revolutionize our energy landscape, offering a clean, virtually limitless power source. For now, it remains a controversial and largely unexplained anomaly. Can materials conduct electricity without resistance at normal temperatures? Superconductivity is a remarkable phenomenon where certain materials, when cooled below a critical temperature, lose all electrical resistance. This means electricity can flow through them indefinitely without any energy loss. However, most known superconductors require extremely low temperatures, making them impractical for widespread use. The quest for room temperature superconductors, materials that exhibit superconductivity at normal ambient temperatures, is one of the holy grails of materials science. If achieved, it would revolutionize technology, leading to lossless power grids, incredibly fast computers, and efficient magnetic levitation transport. While some materials have shown hints of high-temperature superconductivity, a true room-temperature superconductor remains elusive, a dream that continues to drive cutting-edge research. How does physical matter create subjective experience? This is perhaps the most profound mystery in all of science. The hard problem of consciousness asks how physical processes in the brain give rise to subjective experience. The feeling of seeing red, the taste of chocolate, the sensation of pain, or the feeling of love. We can map brain activity, identify neural correlates of consciousness, and understand how information is processed. But how does this physical activity translate into the rich, inner world of our conscious experience? Why do we have qualia, subjective qualities of experience? Is consciousness an emergent property of complex neural networks, or is it something more fundamental? The hard problem challenges the very foundations of neuroscience and philosophy, pushing us to confront the limits of our materialist explanations. Why are physical constants so perfect for life? When we look at the fundamental constants of physics, such as the strength of gravity, the mass of the electron, or the cosmological constant, we find that their values are incredibly precise. If these constants were even slightly different, the universe as we know it, with stars, galaxies, and life, would not exist. This apparent fine-tuning of the universe for life is a profound mystery. Is it a mere coincidence? Is it evidence of a divine creator? Or is it a consequence of the multiverse theory, where our universe is just one of many, and we simply find ourselves in a universe where the conditions are right for our existence? The fine-tuning problem forces us to confront the deepest questions about the nature of reality and the possibility of purpose in the cosmos. How did life emerge from non-living chemicals? One of the most fundamental questions in biology is how life began on Earth. The theory of abiogenesis proposes that life arose from non-living matter through a series of natural chemical processes, but the precise steps involved remain largely unknown. How did simple inorganic molecules combine to form complex organic molecules like amino acids and nucleotides? How did these molecules then self-assemble into self-replicating systems, like RNA or DNA? What were the conditions on early Earth that favored this transition? Was it in primordial soups, hydrothermal vents, or deep beneath the surface? The origin of life is a complex puzzle, requiring insights from chemistry, geology, and biology. A quest to understand the very first spark of existence. What is it, and how does the brain generate it? While we touched upon the hard problem of consciousness in physics, the biological aspect focuses on the neural mechanisms. How do billions of neurons firing in complex patterns give rise to our subjective experience, our sense of self, our thoughts, emotions, and perceptions? Is there a specific region of the brain responsible for consciousness, or is it an emergent property of the entire network? What is the relationship between brain activity and conscious experience? The study of consciousness is an interdisciplinary field, drawing on neuroscience, psychology, philosophy, and even physics, a quest to understand the most intimate aspect of our existence. Why do we dream, and what is their purpose? For millennia, humans have been fascinated by dreams, interpreting them as messages from the divine, glimpses into the future, or reflections of our subconscious desires. Modern science has shed some light on the physiological processes of dreaming, linking it to REM sleep. But the ultimate purpose of dreams remains a mystery. Are they simply random neural firings? Do they play a role in memory consolidation, emotional regulation, or problem solving? Do they help us process trauma or rehearse social interactions? The elusive nature of dreams continues to captivate researchers, a nightly journey into the depths of our own minds. How does belief heal the body? The placebo effect is a remarkable phenomenon where a patient experiences a real improvement in their condition after receiving a treatment that has no active therapeutic component, simply because they believe it will work. This powerful effect demonstrates the profound connection between the mind and the body. But how does it work? What are the neurobiological mechanisms by which belief can trigger physiological changes, reduce pain, or even alleviate symptoms of disease? Understanding the placebo effect could unlock new avenues for treatment, harnessing the body's own healing capabilities. It's a testament to the power of the mind, a mystery that challenges our conventional understanding of medicine. Why do we age, and can it be stopped? Aging is a universal biological process, a gradual decline in physiological function that eventually leads to death. But why do we age? Is it an inevitable consequence of cellular damage accumulating over time? Or is it a programmed process, an evolutionary trade-off? Scientists are exploring various theories of aging, from telomere shortening and oxidative stress to cellular senescence and genetic programming. Can we slow down, stop, or even reverse the aging process? The quest for anti-aging therapies is a rapidly developing field, promising not just longer lifespans, but healthier ones. The mystery of aging is a fundamental biological question with profound implications for human health and society. Do animals experience consciousness like humans? While we can observe animal behavior and infer their mental states, the question of animal consciousness remains a profound philosophical and scientific debate. Do animals have subjective experiences, self-awareness, and the capacity for complex emotions? While it's clear that many animals exhibit sophisticated cognitive abilities, proving consciousness is challenging. The study of animal cognition and behavior, from tool use in crows to complex communication, in dolphins, continues to push the boundaries of our understanding, forcing us to reconsider our place in the animal kingdom and the very definition of consciousness. The vast, unseen world within us and its influence. Our bodies are home to trillions of microorganisms, bacteria, viruses, fungi, and other microbes, collectively known as the microbiome. This vast, unseen ecosystem, particularly in our gut, plays a crucial role in our health, influencing everything from digestion and nutrient absorption to immune function, mood, and even behavior. But we are only just beginning to understand the full extent of its influence. How do these microbial communities interact with each other and with our bodies? How do they contribute to health and disease? The microbiome is a complex and dynamic ecosystem, a hidden world within us that holds immense potential for new medical treatments and a deeper understanding of human biology. How do experiences change gene expression? Epigenetics is the study of heritable changes in gene expression that occur without altering the underlying DNA sequence. It shows how environmental factors, lifestyle, and even experiences can switch genes on or off, influencing our traits and health. For example, diet, stress, and exposure to toxins can leave epigenetic marks on our DNA, which can even be passed down to future generations. This challenges the traditional view of genetics as solely determined by DNA sequence. How do these epigenetic mechanisms work? What is the full extent of their influence on development, disease, and evolution? Epigenetics reveals a dynamic interplay between our genes and our environment, adding another layer of complexity to the story of life, the ultimate cure for this complex disease. Cancer remains one of the most devastating diseases, a complex and multifaceted challenge that continues to baffle medical science. While significant progress has been made in understanding its causes and developing treatments, a universal cure remains elusive. Why do cells lose control and grow uncontrollably? Why does cancer metastasize? Why do some cancers respond to treatment while others resist? The diversity and adaptability of cancer cells make it a moving target. The quest for a cure involves understanding the intricate molecular mechanisms of cancer, developing personalized therapies, and harnessing the power of the immune system. It's a battle on many fronts, a relentless pursuit to conquer one of humanity's greatest scourges. Why did sexual reproduction become dominant? Asexual reproduction, where an organism produces offspring without a partner, seems more efficient. It avoids the costs of finding a mate and only passes on successful genes. Yet, sexual reproduction, with its complexities and risks, is the dominant mode of reproduction for most complex life forms. Why? The leading theory is that sexual reproduction, by shuffling genes and creating genetic diversity, provides a crucial advantage in the face of constantly evolving pathogens and changing environments. it allows populations to adapt more quickly. But the precise evolutionary pressures and mechanisms that led to the dominance of sex remain a fascinating mystery, a fundamental question about the strategies of life. Why isn't photosynthesis more efficient? Photosynthesis, the process by which plants convert sunlight into energy, is the foundation of almost all life on Earth. It is a marvel of biochemical engineering. However, it is surprisingly inefficient, converting only a small fraction of the available solar energy into biomass. Why isn't it more efficient? Are there fundamental physical or biochemical limits? Or could there be ways to engineer more efficient photosynthetic systems, perhaps inspired by nature's own solutions? Understanding the limitations of natural photosynthesis and finding ways to improve it could revolutionize agriculture and renewable energy, addressing some of humanity's most pressing challenges. How are memories formed, stored, and retrieved? Our ability to remember is fundamental to who we are, shaping our identity, learning, and experiences. But how does the brain accomplish this incredible feat? How are fleeting sensory inputs transformed into lasting memories? Where are memories stored? In specific neurons or distributed across networks? And how do we effortlessly retrieve them, sometimes years later? The mechanisms of memory formation, consolidation, and retrieval involve complex interplay between different brain regions and molecular processes. While significant progress has been made, the precise neural codes and cellular changes that underpin memory remain a profound mystery, a quest to understand the very essence of our cognitive selves. Is our sense of choice an illusion? The concept of free will, our ability to make choices and control our actions, is central to our legal systems, moral codes, and sense of personal responsibility. However, modern neuroscience and physics raise challenging questions about its existence. If our brains are physical systems governed by the laws of physics, and if every thought and action is the result of prior causes, then are our choices truly free, or are they predetermined? Some experiments suggest that brain activity associated with a decision can be detected before we are consciously aware of making that decision. This philosophical and scientific debate explores the deepest implications of determinism versus free will, challenging our fundamental understanding of agency and responsibility. How does it distinguish self from non-self so perfectly? Our immune system is an incredibly complex and sophisticated defense network, capable of distinguishing between our own healthy cells, self, and foreign invaders like bacteria and viruses, non-self. This ability to recognize and eliminate threats while tolerating our own tissues is crucial for health. But how does it achieve this remarkable feat with such precision? How does it learn to recognize new pathogens while avoiding autoimmune attacks? The intricate signaling pathways, cellular interactions, and genetic mechanisms that govern immune responses are still being unraveled. Understanding the immune system is key to developing new treatments for infections, autoimmune diseases, and cancer. A quest to master the body's own internal defense force. Why can some animals regenerate limbs, but humans cannot? The ability to regenerate lost body parts, such as limbs, organs, or even entire heads, is common in many animals, from starfish and salamanders to some fish. Yet, humans and most mammals have very limited regenerative capabilities, primarily restricted to wound healing and tissue repair. Why this difference? What are the genetic and cellular mechanisms that allow some animals to regrow complex structures while others cannot? Unlocking the secrets of regeneration could revolutionize medicine, leading to new treatments for spinal cord injuries, organ damage, and limb loss. It's a fascinating biological mystery, a quest to understand the hidden potential within our own genetic code, the ultimate frontier of neuroscience. Despite centuries of study, the human brain remains the most complex object in the known universe, and arguably the ultimate frontier of scientific exploration. With its billions of neurons and trillions of connections, it gives rise to our thoughts, emotions, memories, and consciousness. But how does it work? How does it process information, learn, and adapt? How do different brain regions specialize while also working together? The challenges of mapping its intricate circuitry, understanding its computational principles, and unraveling the mysteries of neurological and psychiatric disorders are immense. The human brain is a universe within itself, a boundless realm of discovery. How do life forms survive in the harshest environments? Extremophils are organisms that thrive in environments once thought to be incompatible with life. Superheated hydrothermal vents, highly acidic lakes, radioactive waste, or deep beneath polar ice. Their existence challenges our assumptions about the limits of life and expands the potential for life beyond Earth. How do these organisms adapt to such extreme conditions? What are the unique biochemical and genetic mechanisms that allow them to survive and flourish where other life forms perish? The study of extremophils provides insights into the resilience of life and offers clues about where to search for life on other planets and moons in our solar system and beyond. Are they alive? Where did they come from? Viruses are enigmatic entities that blur the line between living and non-living. They are obligate intracellular parasites, meaning they can only replicate inside living cells. They lack the cellular machinery for metabolism and reproduction, leading to debate about whether they should be considered alive. But where did they come from? Did they evolve from free-living cells that lost most of their cellular components? Or did they originate from escaped genetic material from cells? The origin of viruses is a complex evolutionary puzzle, with implications for understanding the early evolution of life and the ongoing co-evolution of viruses and their hosts. Why do we need it, and what happens during it? Sleep is a fundamental biological process essential for our physical and mental health. Yet, despite its universality, the precise reasons why we need to sleep and what exactly happens during it remain largely mysterious. Is it for energy conservation, memory consolidation, waste removal from the brain, or emotional regulation? While we know that sleep deprivation has severe consequences, the exact functions of different sleep stages and the molecular mechanisms that regulate sleep are still being unraveled. The mystery of sleep is a nightly journey into the unknown, a vital process that continues to elude a complete scientific explanation. How did it evolve, and why is it unique? The ability to use complex language is a defining characteristic of humanity, setting us apart from all other species. But how did this remarkable capacity evolve? Was it a sudden mutation, or a gradual process driven by social and cognitive pressures? What are the genetic and neural underpinnings of language? And why is human language so uniquely complex with its recursive grammar and vast vocabulary? The evolution of language is a multidisciplinary puzzle, drawing on linguistics, anthropology, neuroscience, and genetics. A quest to understand the origins of our most powerful tool for communication and thought. What are the exact dynamics of our planet's heart? Deep beneath our feet lies Earth's core, a region of extreme temperatures and pressures, composed primarily of iron and nickel. It consists of a solid inner core and a liquid outer core, whose convection currents generate Earth's magnetic field. But the exact dynamics of the core, its precise composition, and its interactions with the mantle remain subjects of intense study. How does the inner core grow? What drives the reversals of Earth's magnetic field? Understanding the core is crucial for understanding plate tectonics, volcanism, and the very habitability of our planet. It's a hidden world, constantly in motion, shaping the surface above. What precisely drives the movement of continents? Plate tectonics, the theory that Earth's outer shell is divided into large plates that are constantly moving, is a cornerstone of modern geology. It explains earthquakes, volcanoes, mountain ranges, and the distribution of continents and oceans. But what precisely drives these massive plates? While mantle convection, the slow churning of molten rock beneath the crust, is the leading candidate, the exact mechanisms and forces involved are still debated. Is it primarily slab pull, where dense oceanic plates sink into the mantle, pulling the rest of the plate along? Or is it ridge push, where new crust formed at mid-ocean ridges pushes plates apart? The precise interplay of these forces remains a complex puzzle, a dynamic dance that continuously reshapes our planet. Can we accurately forecast earthquakes and volcanic eruptions? Earthquakes and volcanic eruptions are powerful and destructive natural phenomena that pose significant threats to human populations. Despite advances in seismology and volcanology, accurately predicting the exact timing and magnitude of these events remains a major scientific challenge. We can identify fault lines and active volcanoes, monitor seismic activity and ground deformation, but reliable short-term predictions are still elusive. What are the subtle precursors that signal an impending event? Can we develop more sophisticated models that integrate diverse data streams? The quest for accurate prediction is a race against time, a scientific endeavor with profound humanitarian implications. How sensitive is Earth's climate to changes? Climate sensitivity refers to how much Earth's global average temperature will rise in response to a doubling of atmospheric carbon dioxide concentrations. It's a crucial parameter for predicting future climate change and its impacts. However, the exact value of climate sensitivity remains uncertain, with different models and observational studies yielding a range of estimates. This uncertainty arises from the complex interplay of various feedback mechanisms in the Earth system, such as clouds, ice sheets, and ocean currents. Understanding climate sensitivity more precisely is vital for making accurate projections and informing policy decisions to mitigate the effects of global warming. It's a complex calculation with global consequences. Where did our oceans come from? Earth is a water-rich planet, with vast oceans covering over 70% of its surface. But where did all this water come from? Was it present during Earth's formation, trapped within the planet's rocky building blocks? Or was it delivered later by comets and asteroids bombarding the early Earth? While both scenarios likely played a role, the precise proportions and timing remain a subject of debate. Recent studies of isotopic ratios in Earth's water and in meteorites provide clues, but a definitive answer is still elusive. The origin of Earth's water is a fundamental question, essential for understanding the habitability of our planet and the potential for water on other celestial bodies. What prevents civilizations from becoming interstellar? The Great Filter is a concept related to the Fermi paradox, proposing that there is some evolutionary or technological barrier that prevents intelligent life from becoming an interstellar civilization. This filter could be in our past, e.g., the extremely low probability of abiogenesis or the emergence of complex life. Or it could lie in our future, e.g., self-destruction through nuclear war, climate catastrophe, or technological singularity. If the filter is in our past, it means life like ours is incredibly rare. If it's in our future, it suggests that most civilizations inevitably face a catastrophic hurdle that prevents them from expanding across the galaxy. The Great Filter is a sobering thought experiment, forcing us to confront the fragility of civilization and the immense challenges that lie ahead. What are the best ways to search for alien technology? Beyond simply searching for signs of life, the concept of technosignatures involves looking for evidence of technology created by extraterrestrial civilizations. This could include radio signals, laser emissions, Dyson spheres, hypothetical megastructures built around stars, or even industrial pollution in exoplanet atmospheres. The challenge lies in knowing what to look for and how to distinguish genuine technosignatures from natural astrophysical phenomena. What are the most efficient strategies for searching across vast cosmic distances? The search for technosignatures is a bold and ambitious endeavor, a quest to find not just life, but intelligence beyond Earth. What makes a planet truly habitable? With thousands of exoplanets discovered, the search for habitable worlds has intensified. But what precisely makes a planet truly habitable? It's more than just being in the Goldilocks zone, where liquid water can exist on the surface. Factors like atmospheric composition, geological activity, the presence of a magnetic field, the stability of the host star, and even the presence of a large moon can all play crucial roles. Understanding the complex interplay of these factors is essential for identifying the most promising candidates for life and guiding future observations. The definition of habitability is constantly evolving, a dynamic concept that reflects our growing understanding of planetary systems. How did our unique moon form? Earth's moon is unusually large compared to its host planet, and its origin has been a long-standing mystery. The leading theory is the giant impact hypothesis, which proposes that the moon formed from the debris ejected into orbit after a Mars-sized protoplanet collided with early Earth. This theory explains many of the moon's characteristics, such as its composition and the Earth-Moon system's angular momentum. However, some aspects of the hypothesis, such as the precise composition of the impactor and the dynamics of the collision, are still being refined. The moon is not just a celestial companion. It plays a crucial role in stabilizing Earth's axial tilt, influencing tides, and potentially facilitating the evolution of life. Its origin is a key piece of Earth's own story. How much life exists deep beneath the surface? For a long time, it was thought that life was primarily confined to Earth's surface and oceans. However, discoveries of vast microbial communities thriving deep within the Earth's crust, in extreme conditions of heat, pressure, and darkness, have revolutionized our understanding of the biosphere. This deep biosphere is thought to contain a significant portion of Earth's total biomass. But how much life is truly down there? What are its limits? How does it survive and evolve in such isolated environments? The study of deep Earth life expands our understanding of the resilience of life and offers clues about where to search for life on other planets and moons, such as Mars or Europa, where subsurface environments might be the most promising habitats. What caused the massive explosion in Siberia? On June 30th, 1908, a massive explosion occurred over the Podkamennaya Tunguska River in Siberia, flattening an estimated 80 million trees over an area of 2,150 square kilometers. The event, known as the Tunguska event, was equivalent to a 10 to 15 megaton TNT blast, yet no impact crater was found. The leading theory is that a large meteoroid or comet exploded in the atmosphere a few kilometers above the surface, causing an airburst. However, the precise nature of the object and the exact mechanisms of the explosion are still debated. Was it a stony asteroid, an icy comet, or something else entirely? The Tunguska event is a powerful reminder of the potential hazards from space and the mysteries that can arise from even relatively recent cosmic impacts. Is there a scientific explanation for its disappearances? The Bermuda Triangle, also known as the Devil's Triangle, is a loosely defined region in the western part of the North Atlantic Ocean where a number of aircraft and ships are said to have disappeared under mysterious circumstances. While popular culture often attributes these disappearances to paranormal activity, extraterrestrials, or unknown forces, scientific explanations typically point to a combination of natural factors. These include the region's frequent severe weather, strong ocean currents, the presence of the Gulf Stream, and the potential for methane hydrate eruptions from the seafloor. However, the enduring allure of the Bermuda Triangle lies in its unexplained nature, a testament to humanity's fascination with the mysterious and the unknown. Was it a message from intelligent life? In 1977, a radio telescope at Ohio State University detected a powerful 72-second-long radio signal from the constellation Sagittarius. The signal was so strong and unusual that an astronomer monitoring the data circled it on a printout and wrote "Wow" next to it. The "Wow" signal had all the hallmarks of a potential message from extraterrestrial intelligence. It was narrow-band, intense, and came from a region of space where no known natural radio sources exist. However, it has never been detected again, despite repeated attempts. Was it a genuine techno-signature, a fleeting message from a distant civilization? Or was it a rare, unexplained natural phenomenon? The "wow" signal remains one of the most intriguing and frustrating pieces of evidence in the search for extraterrestrial intelligence, a cosmic whisper that continues to echo in our minds. How do planetary magnetic fields arise? Magnetic fields are crucial for protecting planets from harmful solar radiation and for maintaining their atmospheres. Earth's magnetic field, generated by the convection of molten iron in its outer core, is vital for our planet's habitability. But how do these planetary dynamos work in detail? What are the precise conditions and mechanisms that lead to the generation and maintenance of strong magnetic fields? Why do some planets have strong fields, while others have weak or no fields? Understanding the origin of magnetism is essential for understanding planetary evolution and the conditions for life. It's a fundamental force that shapes worlds. How will melting ice caps impact the planet? Earth's cryosphere, which includes all the frozen parts of our planet, glaciers, ice sheets, sea ice, and permafrost, plays a critical role in regulating global climate and sea levels. However, with rising global temperatures, the cryosphere is undergoing rapid changes, with ice caps melting at an accelerating rate. How will these changes impact global sea levels, ocean currents, weather patterns, and ecosystems? What are the tipping points beyond which these changes become irreversible? The future of the cryosphere is a complex and urgent scientific question, with profound implications for human societies and the natural world. It's a stark reminder of the interconnectedness of Earth's systems, the complex dance of global water movement. The world's oceans are crisscrossed by vast, intricate systems of currents, both at the surface and in the deep. These currents play a crucial role in distributing heat around the globe, influencing climate, weather patterns, and marine ecosystems. But the precise dynamics of these global ocean currents, their interactions, and their long-term variability are still not fully understood. How do they respond to changes in temperature, salinity, and wind patterns? What are the implications of a changing climate on these vital oceanic conveyor belts? The study of ocean currents is a complex and multidisciplinary field, a quest to understand the hidden engines that drive our planet's climate system. What are the true dynamics of Earth's radiation belts? The Van Allen belts are two concentric rings of energetic charged particles that are trapped by Earth's magnetic field. They protect Earth from harmful solar radiation, but they also pose a hazard to spacecraft and astronauts. While we have a general understanding of their existence, the precise dynamics of the Van Allen belts, how particles are injected, accelerated, and lost, are still being studied. How do they respond to solar storms and space weather? Can we predict their behavior more accurately? Understanding the Van Allen belts is crucial for safe space exploration and for protecting our technological infrastructure in orbit. High-energy radiation from thunderstorms, dark lightning, or terrestrial gamma-ray flashes, TGFS, are brief bursts of high-energy gamma rays that originate from thunderstorms. These flashes are incredibly powerful, yet they are invisible to the naked eye. Hence the name dark lightning. How are these bursts generated? What are the precise mechanisms that accelerate electrons to relativistic speeds within thunderclouds, producing such intense radiation? TGFS are a relatively recent discovery, and their study is revealing new insights into the extreme physics occurring within thunderstorms. They are a powerful reminder that even familiar phenomena can harbor hidden, energetic secrets. What causes the constant low-frequency vibration? For decades, seismologists have detected a faint, continuous, low-frequency vibration emanating from Earth, often referred to as the Earth's hum. This persistent background noise is too low in frequency to be heard by human ears, but it can be detected by sensitive seismometers. What causes this mysterious hum? While various theories have been proposed, including interactions between ocean waves and the sea floor, and atmospheric turbulence, The precise source and mechanisms are still debated. The Earth's hum is a subtle but pervasive phenomenon, a constant whisper from our planet that continues to elude a complete explanation. While we touched upon abiogenesis earlier, the specifics of how it happened remain a complex tapestry of unsolved questions. Was it the RNA world hypothesis, where RNA, not DNA, was the primary genetic material and catalyst? Did life originate in alkaline hydrothermal vents, providing the necessary chemical gradients and energy? Or was it a combination of factors, perhaps involving clay minerals acting as catalysts or meteorites delivering organic compounds? Each theory offers compelling pieces of the puzzle, but the complete step-by-step narrative of life's genesis remains one of science's most profound and intricate mysteries. It's a story that continues to unfold, revealing the astonishing ingenuity of nature. While we discussed the hard problem, the biological and evolutionary origins of consciousness remain deeply mysterious. How did the complex neural networks of the brain evolve to produce subjective experience? Is it a continuous spectrum across species or a uniquely human trait? What are the evolutionary advantages of consciousness? This question delves into the very essence of what it means to be aware, a profound inquiry into the biological roots of our inner world. Beyond their purpose, the actual mechanisms of dreaming are still largely unknown. How does the brain construct such vivid, often bizarre, narratives during sleep? What neural circuits are active, and how do they interact to create these immersive experiences? Are dreams merely a byproduct of brain activity, or do they serve a more active role in maintaining mental health and cognitive function? The nocturnal theatre of our minds continues to be a frontier of neuroscience. The power of belief to heal is undeniable, but the full extent of its neurobiological pathways is still being mapped. How does the brain release its own pain-relieving chemicals, like endorphins, in response to a placebo? What role do expectations and conditioning play? Can we harness the placebo effect more effectively in clinical settings? And what does it tell us about the mind-body connection? This mystery challenges the boundaries of conventional medicine. While we know aging is a complex process, the precise interplay of genetic, environmental, and lifestyle factors that determine individual longevity is still being unraveled. Why do some individuals live to be over 100 with remarkable health, while others succumb to age-related diseases much earlier? Are there specific genes or pathways that can be targeted to extend healthy lifespan? The quest for the secrets of longevity is a race against time, promising a future where aging is no longer an inevitable decline. Beyond consciousness, the diversity and complexity of animal intelligence continue to surprise us. How do octopuses solve puzzles? How do birds navigate thousands of miles with incredible accuracy? How do chimpanzees learn and use tools? While we can observe these behaviors, understanding the underlying cognitive processes and their evolutionary drivers remains a challenge. The study of animal minds forces us to expand our definitions of intelligence and rethink our place in the animal kingdom and the very definition of consciousness. The intricate relationship between our gut microbiome and nearly every aspect of our health is a rapidly expanding field of research. How do specific microbial species influence our immune system, metabolism, brain function, and susceptibility to disease? Can we manipulate the microbiome through diet, probiotics, or fecal transplants to treat a wide range of conditions. The human body is a superorganism, and understanding its microbial inhabitants is key to unlocking new frontiers in personalized medicine. The idea that environmental experiences can leave heritable marks on our genes, influencing future generations, is revolutionary. How precisely are these epigenetic tags passed down? What are the long-term implications for human health and evolution? Can we reverse undesirable epigenetic changes? This field challenges the traditional view of genetic determinism, revealing a more dynamic and responsive genome that interacts intimately with its environment. The biggest challenge in treating cancer is its incredible heterogeneity and ability to evolve resistance to therapies. Why do cancer cells within the same tumor behave so differently? How do they develop mechanisms to evade drugs and the immune system? Understanding the evolutionary dynamics of cancer and its ability to adapt is crucial for developing more effective and durable treatments. It's a complex arms race between medicine and disease. In a world often seen as driven by competition and survival of the fittest, the widespread existence of cooperation, altruism, and social behavior across the animal kingdom is a profound evolutionary puzzle. How did these behaviors evolve? What are the genetic and environmental factors that favor cooperation over selfishness? From ant colonies to human societies, understanding the evolution of cooperation is key to understanding the fabric of social life. The debate over whether viruses are alive or not continues to shape our understanding of life itself. If they are not alive, how did they acquire the ability to replicate and evolve? If they are, what does that tell us about the minimal requirements for life? The study of giant viruses, which possess complex genomes and some cellular machinery, further blurs these lines, suggesting a more intricate evolutionary history for these ubiquitous biological entities. Pain is a fundamental, often debilitating human experience, essential for survival, but also a source of immense suffering. What are the neural pathways and psychological factors that contribute to the perception of pain? Why do some individuals experience chronic pain without obvious physical injury? How can we effectively manage and alleviate pain without harmful side effects? The mystery of pain delves into the complex interplay of biology, psychology, and subjective experience. This overarching philosophical question is fueled by many of the scientific mysteries we've explored. If life is common, why haven't we found it? If consciousness is an emergent property, could it arise elsewhere? The more we learn about the universe, the more we are forced to confront our own significance or insignificance in the grand scheme of things. It's a question that continues to shape our worldview and drive our exploration. The history of science is a testament to humanity's insatiable curiosity and capacity for discovery. But what unknown unknowns lie ahead? What fundamental laws or phenomena are yet to be uncovered? The very nature of scientific progress means that the biggest mysteries are often those we haven't even conceived of yet. This mystery is a hopeful one, a promise of endless wonder and the continuous expansion of our knowledge. This question transcends individual scientific disciplines, touching upon philosophy, physics, and consciousness. Is reality a simulation? Is it fundamentally digital or analog? Are our perceptions merely a limited interface to a much grander truth? This ultimate mystery invites us to question everything, to look beyond the surface and to ponder the very fabric of existence. The final mystery is not a specific phenomenon, but the enduring human capacity for wonder in the face of the unknown. Despite all our scientific advancements, the universe continues to present us with questions that defy easy answers, phenomena that challenge our paradigms, and experiences that push the boundaries of our understanding. This persistent sense of mystery is not a failure of science, but its greatest triumph. For it is in the pursuit of these unanswered questions that we truly grow, learn, and evolve.